Hey everyone, welcome to Introduction to Cognitive Science. I'm Adam, and the focus of our lecture today is on artificial intelligence, Turing machines, and neural networks. The article that we read for today was entitled Computational Modeling of the Mind, published in the journal Wire's Cognitive Science by Michael Rescorla in 2015. Today, we'll look at some important parts of the article, as well as related material on Turing machines and neural networks. So what is artificial intelligence? Well, artificial intelligence can be distinguished into weak or narrow AI and strong or general AI. Weak or narrow artificial intelligence refers to machines or programs that can perform very well on single specific tasks or in single domains of intelligence. So, for example, we often think of the ability to play a game well, a game like chess, as requiring intelligence. So, we've seen the development of different programs that are able to perform incredibly well on these specific games. So, for example, Lebratus is excellent at playing poker. BKG 9.8 is excellent at playing backgammon. Deep Blue is excellent at playing chess. And AlphaGo is excellent at playing Go. In fact, these programs are so excellent in their single tasks or in their single domains of intelligence that they outperform humans, the best humans in these games. So although that's remarkable in that we're able to build machines or programs that demonstrate weak or narrow AI, we see that these programs are not able to perform well on a variety of different tasks. In other words, these programs do not demonstrate strong or general intelligence. So for example, AlphaGo it performs incredibly well at the game of Go. However, AlphaGo does not perform well on chess, backgammon, or poker. Similarly, AlphaGo can't tell jokes or juggle or do tricks on a skateboard or any of the other different tasks that humans can engage in. So we see that programs like Deep Blue and AlphaGo, although remarkable achievements in the sense of weak or narrow AI, those programs aren't reaching the level of strong or general intelligence. Okay. Strong or general artificial intelligence refers to machines and programs that can perform well on a variety of different tasks. Machines or programs with strong or general artificial intelligence demonstrate intelligence in multiple domains, not just a single domain. Okay, so an example of such a machine would be us, humans. We can solve math problems, physics problems, we can tell jokes, we can play games, we can juggle, do tricks on a skateboard, cook, engage in spatial navigation, all sorts of different tasks. So we demonstrate intelligence in a more general and stronger sense. Okay. One of the major missions in computer science and artificial intelligence is to go from the ability to create weak or narrow artificial intelligence systems to be able to create strong or generally intelligent artificial systems, right? So the goal is to go from having programs like AlphaGo to having programs like a human, in which we can have programs that engage in multiple tasks. Okay, we can see that this would be very useful for practical purposes, right? Maybe this could serve, help the elderly, right? In keeping them company, engaging in novel, interesting conversations, helping them practically with different tasks around the house, and so on. In one of the supplementary videos that I had you watch, we see that some engineers and scholars assert that we're already at the stage of having strong or general AI. So one of the engineers from Google, or one of the employees at Google, claims to have encountered an artificially intelligent agent that is sentient or conscious. So, one of the goals in computer science and AI is to go from weak or narrow AI to strong or general AI, but there's debate in the field on how far along we are to getting there. Okay, many engineers and scholars are going to claim that we're not there yet. We're still at the level of developing weak AI, but not strong AI. But there are an increasing number of people that are claiming that we're at that stage of now having strong or general AI with us. Okay, so I think that this is a very fascinating, interesting time to be alive. The gap between human and machine intelligence is becoming fuzzier and more interesting. Okay, so now we have an idea of the distinction between weak or narrow AI, right? Like single domain intelligence and strong or general AI, right? Intelligence in the broader sense of multiple domains of intelligence. So now that we have an understanding of strong and weak AI, another question is, how do we build intelligent systems? We'll look at two approaches, the Turing machine approach and the neural network approach. The classical computational theory of mind, also called classical computationalism or CTM, holds that many important mental processes, cognitions and computations, are like those executed by Turing machines. A Turing machine is an abstract mathematical model of an idealized computing device that was introduced by Alan Turing. And here we see an example of a Turing machine up here at the top. This is the mathematical model or the abstract model. And down here we see physical instantiation in a Turing machine that someone built. So we see that a Turing machine contains a central processing unit or a CPU right here, and memory storage with memory locations. And that's provided right here. Okay, so this is like tape with cells on the tape. Okay, and this could be like the human analog of this would be like our long-term memory. Okay, like a memory tape right here. Okay. Turing describes these memory locations as cells on a two-way paper tape, but one might physically realize memory locations using other media, such as vacuum tubes, silicon chips, and other media. In other words, a Turing machine can be multiply realized, right? A Turing machine can be realized in different sorts of things. For example, in this physical system, but it also might be the case that a Turing machine is realized in our biological brain. A Turing machine manipulates primitive symbols from a finite alphabet. The central processor inscribes or erases symbols in memory locations, depending on the current contents of a memory location and the current state of the processor. A machine table encodes precise rules, dictating how the central processor should proceed. Let's look at an example of a simple Turing machine on the next slide to get a good feel of how a Turing machine works. All right, so imagine we want to perform an erase or clear all function and return this tape so that it shows all zeros. So I've provided for you right here on this left-hand side of the slide, a sample memory tape with some symbols inscribed on it. Okay, So we'll see down here, this is the memory tape. We see that it starts here. There's a start state, right? And then we have cells. And in each cell, I've inscribed a symbol from the finite alphabet, okay? And it's just zeros and ones in this case, okay? And then we also have this right here, which is where we'll halt, okay? So this just means that there's no symbol here. There's no symbol from the alphabet, so there's no 1 or 0. So when we get here, we'll halt, okay? So we have our memory tape, and we have on top of this tape, so like the tape is here, and I represented that right here, okay? And then we have a head, which we see on that sort of scrolls over the tape, okay? And the head is going to sort of go over each cell, cell by cell, right? And it'll perform an operation on the cell, depending on what the CPU with the machine table dictates, okay? The CPU, we see that the CPU is right here, the central processing unit. The CPU is going to contain a machine table, and the machine table has rules in it. Okay, this is an example of some rules, but I've provided a simple set of rules right here for us to look at. Okay, and the rules are the following. If we see a 0, then we'll leave it and move over 1 cell to the right. If we see a 1, then we'll erase the 1, write a 0, and then move over to the right. If we see a blank cell, then we'll halt and we'll stop. Okay, cool. Now all we have to do is follow the rule in a step-by-step manner. Okay, so we'll start at the start state, right? And we'll just execute the rules. So we see that there's a 0 here. So the rule says if 0, then move right. Okay, so we'll leave this 0, move over 1 cell to the right. Okay, cool. Now we see on the next cell that we see 0 again. So it says if 0, leave it, move to the right. All right, so now we're at the next cell. We see that once again, this cell says if 0, leave it, then move to the right. All right, now we're at this cell. It says if 1, then erase 1 and write 0, then move to the right. Okay, so that's what we'll do here. We'll erase this 1, replace it with the 0, then move over to the right. Okay, so now the head is over this right here, this cell. Okay, we see in this cell that there's a 1 again. And our rule is if 1, erase it, write a 0, move over to the right. Okay, now we're on this cell. The head is over this cell. We see that it's a 0. So if 0, leave it, move to the right. So we move the head over 1 cell. We're on this cell now that is a 1. And our rule is if 1, erase it, write a 0, move over to the right. Okay, now we're on this cell. It's a 0. Our rule is if 0, then move over to the right. We're on this cell now. The head is over on this cell. We see that it's a 1. The rule is if 1, erase it, write a 0, move over to the right. We're on this cell now. The head is over this cell. We see that it's a 0. Our rule is if 0, leave it, move to the right. And then finally, we get to a blank cell. And so we halt based on this rule. If blank, halt. And now our operation has stopped, okay? After the Turing machine has completed performing these operations or computations or cognitions, we have as a result this, right? And we see down here that now we've removed all the 1s from our string, okay? And we're left with all 0s. So we've performed our operation, which is erase or clear all, okay? So sweet. We see that this is just a very simple example of how we can perform a computation or cognition, right? Like erase all, okay? And the insight here is we're performing this computation or cognition in a step-by-step manner based on these rules that are included in the CPU, right, in the machine table in the CPU. Although this is a simple example, the main idea behind Turing machines is that computations are rule-governed manipulations of symbols inscribed in a read and write memory. Turing argued that this model can replicate any humanly executable mechanical procedure for manipulating symbols. You might think that knowing a language or knowing how to play a game consists of such a set of rules, right? You might think that a master chess player has these rules in their mind. And when they're playing chess, they're executing these rules in a Turing machine-like manner. That's the main idea here. According to classical computationalism, or the classical computational theory of mind, the human mind works precisely in this way, like a Turing machine or a traditional computer program, by performing computations in a rule-governed, syntactically acceptable manner via manipulations of symbols that are stored in human long-term memory. Okay, and the analog of a symbol from the Turing machine will be something like a mental symbol or concept in the human mind. This computational view of the mind played an especially important role in the early days of cognitive science in the 50s, 60s, and 70s, but continues to remain influential even to this day. So we have one approach to building intelligent systems based on Turing machines. We also have another approach to building intelligent systems based on neural networks. One important thing that we saw from Turing machines was that Turing machines are based on explicit rules, right? So we saw that the explicit rules were included in the machine table in the CPU. Okay, so Turing machines are based on explicit rules and correspond to the traditional computer program approach, right? So we have a set of rules in the mind, and then we have input, and based on the input, like sensory input and whatnot, and the rules in the mind, we then produce an output, okay? And that's the traditional approach. Okay, another way to put this is data or input plus rules equals the output on this view, okay? And here what we're emphasizing is that the input is sort of given and the rules are sort of given, right? And given the input and the rules, we then produce an output, okay? This is going to be very different than the approach adopted by neural networks, okay? In neural networks, what we're going to do is we're going to have inputs and outputs, right? And then from those, a large amount of inputs and outputs, we will derive a rule, okay? So on this alternative view, the rule is not included as given, but that's the thing that we're going to derive or we're going to get, okay? So that's why here on the machine learning approach, we see data or input plus output, and from that we'll get a rule or a program. Okay, that's the important thing here. Really, the emphasis I want to emphasize is where the rules go, right? In traditional computer programming and Turing machines, the rules are included, right? Like you can think I'm born innately with rules for language or whatnot. Okay. On the other view, here, machine learning, neural networks, the rules, I'm not born with rules, but rather based on lots of input and outputs, I'm able to derive such a rule. Okay, and we'll look in subsequent slides at how this works for neural networks. So whereas Turing machines are based on explicit rules and correspond to the traditional computer programming approach, connectionism is based on neural networks and corresponds to the machine learning approach. We just looked at Turing machines' explicit rules and traditional computer programming. So next, let's take a look at connectionism, neural networks, and machine learning. According to connectionism, the mind consists of neural networks that are composed of units along with weights that measure the strength of connections between units. In an artificial neural network, we have input units, which are analogous to sensory neurons located here in this input layer. We see the input units here, and we just call this the input layer. Okay, the input layer includes the input units. Over here, we have output units, and these are analogous to motor neurons, right? And the output units are within the output layer, okay, on the other end. And in between the input layer and the output layer, we have hidden layers. And the hidden layers include the hidden units. Okay, and hidden units are analogous to interneurons, which connect between the input layer here and the output layer here. Okay, and a deep neural network is just an artificial neural network that has many hidden layers. Weights refer to the strength of the connection between the units. Okay, so between these two units, we see a connection represented by this line, and it can be weighted either in a positive way or a negative way. All right, we can have a positive weight, which represents activation of the receiving unit by the activity of the sending unit. We also have negative weights, which represent inhibition of the receiving unit by the activity of the sending unit. Okay. And we can see that these hidden layers can code or stand for different properties. Okay, so we might feed an image, such as of a face, a human face, or of a cat, or of a dog. In this first hidden layer, it's to capture the edges in the photo. Okay, so there's going to be fine grain edges within this photo, and the goal of the first layer is to capture these edges. In this next layer, we're going to capture combinations of edges. Okay, and then the next layer still will capture combinations of edges, or an object model. Okay. And the goal is, as we feed an image here, we should be able to get identification of whether that image is of a human face or of a cat or of a dog. So a system that maps an input to an output needs training to do this in a useful way. Just as people need to be trained to perform tasks, such as improving their ability to hit a target with a bow and arrow, machine learning systems need to be trained to improve their performance also. So you can think about Hawkeye here. On that first shot, imagine like Hawkeye's learning, right? Of course, he's excellent right now, but imagine in the very beginning days, like the very first time Hawkeye shot, it probably didn't land straight in the middle, right? There's going to be there's going to be an initial shot, and then based on how far off you are, you're going to make some corrections, right? So maybe the first time you shot the arrow, it's a little too low, right? So now you know, okay, I got to correct. So you move up. Now you shoot, and now it's a little bit too high, right? So, okay, I corrected a little bit too much. So let me correct again, right? And through more data, right, as you take more shots and you see where they land, you'll increasingly fine tune your positioning until you can start hitting that bullseye right in the center. okay? Similarly, machine learning is going to be more accurate at predicting cats versus dogs and so on, the more that we train this, like the more data that these systems are trained on, okay? Training is accomplished by giving the system an input and the corresponding output and modifying the structure in the learning machine so that the appropriate mapping is learned. This is similar to curve fitting or regression. If we have enough training pairs, then the system will be able to produce correct outputs when new inputs are introduced. And we'll take a look at an example right here. All right, so we see here that supervised learning systems, and we'll talk about supervised learning systems. This has to do with using labeled data, but supervised learning systems all exemplify the function approximation problem, where the training data take the form of a collection of XY pairs, and the goal is to produce a prediction Y in response to a query X. Okay, so let's go ahead and look at this sample figure that I have here, which is reported happiness as a function of income, right? Based on how much income you make, how happy are you, right? And this isn't accurate. This is just, we're just using this as a little toy model, okay? I don't think that happiness is a direct relation. It's not directly related to income in this way. So, but just for fun, let's use this as a model to work with, okay? What is the rule relating income and happiness? We might have such a question, right? What is the rule relating these two things? It's hard to think of a rule in the traditional programming sense for this, but maybe we can derive a rule from lots of data. Okay? So what we could do in this case, maybe we don't know at the outset what the rule is for relating these two things, right? What we can do is we can ask a lot of people. Maybe there's census data that we can draw upon where we know how much people make, and then we can have them rate on a scale how happy they are, right? So for example, we're using a happiness scale of 0 to 10. Okay, so we get like lots of people and we just ask them, how happy are you on a scale of 1 to, or on a scale of 0 to 10? And a lot of people are going to fill out this survey. Then we can see how much money they make. Okay, and then we can start to plot this data, right? Like based on how much income you make. Say you make $20,000, for example, right? You're right here on the x-axis, and then, you know, your response, for example, say that you answered that, well, your happiness is 1.62, for example. That might be one data point, okay? Person A that took the survey, they made $20,000 a year and they rated their happiness as a 1.62 out of 10, okay? And just for example, say that we conduct this survey and we get all these data points here, right? Someone that made $30,000 rated their happiness at 2.33. Someone that makes $40,000 a year rated their happiness 3.04, and so on throughout here, okay? What we see as we plot all these points, right? We see that at some point we can draw a line, right? We can draw a nice line through our data points, right? We can perform linear regression here, right? And we can see that we now have derived a rule from the data, right? That's what we're talking about with machine learning, is rather than starting with this rule right here, right? Rather than starting with this rule, if we have like a billion or a trillion data points, right? We can plot the data, right? Like income and happiness scores, like a billion of those, and then draw the best line through that, right? Perform a linear regression, draw a nice line through there. And now we've derived the rule from there. Something like a rule. Notice that it may not predict perfectly, right? but it will give us a very good estimate or guesstimation. Okay. And this is how we predict the weather. There is no like strict, simple rule to calculate the weather for tomorrow. But given lots and lots of data, we can make better and worse predictions of what the weather will be tomorrow. Okay. We can draw a line through data to find our best predictions. And that's what we're doing here. Okay. And importantly, once we have enough data, we can start to make predictions for things that we don't have data on, right? That's sort of another important insight here, is that notice that in the example, I've pointed out that, for example, we've collected data from people that make up to $110,000 a year, but we can then ask, right, from this data and the rule we derive from the data, we can then guess, well, what if someone makes $120,000? Like, what if you get a raise next year and your pay goes up to 120,000? What would we predict your change in happiness would be, right? And now we can make a prediction, right? Even though we never sampled someone that made that much, based on all our data, we can predict that someone that makes $120,000 a year would rate their happiness in 8.72 out of 10. All right. So that's going to be the insight here on machine learning and connectionism, neural networks. We're getting a rule, right? We're using inputs and outputs, right? We're using inputs and outputs to get a rule with machine learning and neural networks. Whereas with Turing machines, we have a rule in the beginning, and we're using inputs and the rule to produce an output. When training artificial neural networks, supervised learning involves labeled data. So we can have humans that label pictures as that's a cat, that's a dog. Okay. For example, supervised learning takes labeled data, such as a database where 10,000 photos have already been labeled as cats and 10,000 photos have already been labeled as dogs. And then supervised learning uses this to predict or classify something new, such as a new photo, whether that photo is a cat or a dog. The data set can be split into training data and testing data. For example, given a large amount of photos, we might train our model with 80% of the photos, but reserve 20% of the photos to test and see how well our model's performing. Okay. And we do this so that way we don't have to deploy our model to see how well it performs. Imagine if you had to deploy something to see how well it worked, right? That would not be cost effective, right? You might have a very horrible model at first, and then if you deploy it into the public and it's a complete failure, it'll cost you a lot of money and people may not use your product anymore, right? So before we deploy the product for good, right, we want to test it first, right? And by having training data and testing data, it'll allow us to check to see how well our model's performing before we deploy it and push it out into the real world. Okay. So with our training data, right, if I have access to a data set, I will not use all the data to train my model, right? I'm going to leave some data out to test my model. Okay. So, the nature of these splits differ. So some people like an 80-20 split. This is going to be slightly case dependent, like also depending on what type of field you're working on. If you're working in music recommender systems, you may have a different criteria than if you're working in like the medical field. Okay. But just to make this easy for today, let's just think about a simple 80-20 split. Okay, imagine I have 100,000 labeled images of cats and dogs. I can use 80,000 labeled images, 80%, for supervised learning to train my model. And my model, what I want my model to do is to identify what image, if the image is showing a picture of a cat or if it's showing a picture of a dog. Okay. This, by using only 80,000 images, this allows me to reserve 20,000 labeled images to test my model and see how well it performs on new images. And by new images, I mean just those images that were not included for training the model to begin with. Okay, so you see the great thing here is that I have access to 100,000 labeled images, right? So I have 100,000 instances where I know whether that image is of a cat or a dog. Okay, now I can use 80,000 to train my model to do something like build this, right? And then I can test my model on new data, right? Data that I have for my data set, but which was not used to train the model, right? So since that data was not used to train the model, I can use it to test my model, right? And so now what I can do is, since we'll just say image number 80,001, right? It wasn't included in the training set. I can now provide that to my object recognition program and see if it correctly identifies that image as of a cat or a dog, right? And say the model that I built off of the 80,000 images identifies that image as a cat, right? I know if it's working correctly because I know, since that image is labeled, I know if it's of a cat or not, right? So because it's labeled, I can know how well my model is performing on the new images. Okay, and what would be excellent is if, based on the 80,000 images I used to train my model, it then correctly identifies all 20,000 images, right? That would be excellent, right? And then I can feel good about deploying such a model in the real world. Okay, however, if the model is not performing well, right? If the testing data, right, if my model is not identifying that correctly, I know I need to make some further adjustments to my model. Okay, there needs to be some reweighting going on here in the hidden layers and things of that nature. Okay. So splitting the data into training and testing data in this way allows us to test the performance of our model with our original data set of 100,000 images before a final deployment, which can be costly. For example, if we give an object recognition system millions or billions of cat images and label those images as cats, then we hope that when it is given a new cat image, it will also recognize that image as of a cat. However, problems can arise when we don't have enough training data. For example, if you only have one photo of a dog and one photo of a cat, you're not going to be able to train your model adequately. Okay. Or another problem is when the training data are not sufficiently diverse. Okay. So for example, even if I have 1,000,000 images of dogs, if it's all of just my dog, right? Like on a specific day, say like the first day I got Loki, 1,000,000 images on my phone, right? Well, that's a lot of data, but it's not diverse data, right? And unfortunately, that's not going to lead to accurate identification of dogs that are of a very different type, right? My model will become super tuned, right, to looking for properties of Loki, right? It'll be overfit to looking for Lokis rather than dogs in general, right? So my model will really be a Loki identification algorithm rather than like a dog recognition algorithm or whatnot. Okay, so two problems, right? Not enough data and data of only a certain kind, limited kind. So our object recognition system may not be able to identify bulldogs, for example, if the training data only included images of yellow labs, Diversifying the training data is very important for a properly functioning neural network, right? One that can identify among various animals, human faces, and so on. When training artificial neural networks, unsupervised learning involves unlabeled data. So we have just discussed supervised learning and how that involves labeled data, but there's different types of learning, and unsupervised learning involves unlabeled as opposed to labeled data. Okay, so for example, unsupervised learning looks for similar statistical properties within unlabeled data to find naturally emerging clusters. Okay, so for example, with the data set of 1,000,000 or 1,000,000,000 or 1,000,000,000,000 unlabeled photos, distinct clusters for cats and dogs may naturally start to emerge. Okay, for example, we may have just like a lot of fruit, right? Just like 1,000,000,000 pieces of fruit or 1,000,000,000,000 pieces of fruit, right? And we may not have any labels for what kind of fruit it is, but just based on the statistics, right, of that these things tend to clump together, cluster together, and in a way that's distinct from these. Like maybe we have oranges, which are very round, and we have like bananas, which are not round, right? So we see that even though we don't have labels for oranges and bananas, based on the statistical properties that they have, the oranges will start to cluster together and the bananas will start clustering together. Even if the oranges and bananas are also of different sizes and slightly different shapes. Like even oranges are not all perfectly the same color, shape, and whatnot. And bananas also differ in their shape and color and whatnot, right? But over many, many, many instances, like 1,000,000,000 or 1,000,000,000,000, right, we can start to cluster them into groups, right, even without a label. Okay. So clustering algorithms are an example of unsupervised learning. Although the images of dogs and cats are not labeled with unsupervised learning, if you provide enough training data, for example, 1,000,000,000 or 1,000,000,000,000 images of cats and dogs, then the images will naturally start to form distinct clusters. So there are different ways to train artificial neural networks, but the important point for our purposes today is that we can use artificial neural networks to build intelligent systems without explicit rules by drawing upon large amounts of data. With increasing accessibility to data, along with increasing computational power due to technological advances, right, thanks to GPUs, TPUs, and so on, we're now in an amazing position to build complex, intelligent systems to help us solve many issues in society and daily life. For example, neural networks have been useful for the development of many advanced technologies, including natural language processing technologies, social robots, autonomous vehicles, and many others. And what we see here in this figure is a very cool photo of Elon Musk's Tesla robot. Okay, so this should be coming out soon. I think the MSRP is like $10,000, but we see that it's fitted with cameras. It has a multicam video neural network, neural net planning, auto labeling, simulation, and other tools. So very cool. The idea is that this will be a robot that we can have in our houses that can help us with different activities of daily living and things of this nature. Some of these technologies are becoming so advanced that it is becoming increasingly difficult to discern whether one is interacting with a machine or a real human being. If you cannot tell whether an agent, we'll call her Amanda, if you cannot tell whether Amanda, this agent that you're talking to, is a machine or a real person, then that agent can be said to have passed the Turing test. And I had you watch a really cool video of this agent having conversations, right? And we see that this agent is able to engage in natural conversation. This agent is able to make jokes and discuss philosophical concepts. The agent also makes minor errors and uses facial expressions. So we see that technology has come along a long way. Some have also suggested an extended version of the Turing test that not only considers communication, but also considers other forms of social behavior, such as facial expressions, bodily behaviors, and so on. Okay, and we're getting to a point where the agents that we engage with online are becoming hard to differentiate, right? Whether they're robots or humans, machines or humans. So we want artificial intelligence or artificially intelligent agents, robots and whatnot to be smart, but shouldn't they be friendly also? What are important qualities of social robots? Scholars working in the field of social robotics have suggested the following qualities for social robots. Okay, so Cynthia Brazil from MIT did some groundbreaking work with this social robot Kismet. Okay, and this has motivated a lot of recent research on how to develop social robots. Okay, the idea here is that we want robots to be intelligent, of course, but also by having robots become more social, it'll help facilitate our natural engagement with these robots. If the robot is completely asocial, right, there's sort of, we don't feel comfortable working with those types of robots. So by making these robots more social, it helps to decrease barriers and accessibility to these robots. So if we want to make a robot not only intelligent, but social, here are some qualities that it should have. Social agents are interactive. So we should build our robots so that they're interactive with us. Social agents show initiative. So we want our robots to also start conversations or initiate engagements in certain ways. Social agents perceive emotions and express emotions. So we want our social robots to be able to perceive our emotions as well as express their own emotions, perhaps through facial expressions and body language. That's one of the things that makes this very convincing, is that there is a good use of facial expressions and natural engagement. Social agents also understand and produce language. So we need our robots to understand the utterances or commands that we produce, as well as produce their own utterances and commands. And social agents use body language, such as gaze, facial expressions, gesture, posture, and movement. And we see Kismet has many component parts, that move, eyebrows, mouth, and so on. Social agents also establish and maintain social relationships. So there was a really cool robot here that was sort of positioned at the mall for a while. And on the first day, it sees somebody new, it'll ask them their name and about some personal features about them. So for example, this lady, on the first day, it asked her her name and so on. Okay, some personal details. The interesting thing is, on subsequent days, like the next day this lady walked by in the mall, the robot remembered her and was able to engage her in conversation, right? Bring up things from the previous conversation and produce utterances that express affection, or like, oh, hey, I remember you from last time. How are you? How was this thing that you were talking about the other day? Right? Oh, so good to see you. I miss you. Right? So things like that, right? By building our robots so that they are able to establish and maintain relationships, we make them more desirable to interact with. And then finally, scholars that work on social robotics have suggested that social agents have some sort of personality. Okay. So my question for you is, what do you think about these qualities? Do you think that any other qualities are important for a social robot? All right, it looks like we're on track to build some truly amazing robots in the future. Perhaps we should prepare ourselves. Let's think about some laws of robotics. Okay, so Isaac Asimov originally proposed 3 laws of robotics and then added a 4th law later. Let's look at the 3 laws, or the 4 laws, and then I'll ask you a few questions to think about. The first law of robotics is that a robot may not injure a human being or, through an action, allow a human being to come to harm. Okay, and we see that here. Okay, robot with the shield as a protector. The second law of robotics is that a robot must obey the orders given it by human beings, except where such orders would conflict with the first law. Okay, so that's here. And then the third law of robotics is that a robot must protect its own existence as long as such protection does not conflict with the first or second law. Okay, and we see here, the robot's protecting itself from the rain. Okay, and then the 4th law, added later, a robot may not harm humanity or by an action allow humanity to come to harm. Okay, so my question for you is, what do you think about these laws? Do you think these laws are necessary? Do you think all these laws are necessary? We need each one of them. Do you think these laws are sufficient? Do you think that these laws are enough? Or do we need additional laws to add to this? Do you think these laws are mutually compatible? Right? When we look at each of these laws, although independently they might sound convincing, are they mutually compatible with each other? For example, a robot may not harm humanity or by an action allow humanity to come to harm. But what if humans are the ones that are causing harm to humanity, right? So there's an issue here where a robot's not supposed to harm humans, but also not supposed to allow humanity to come to harm. But what if humans are harming humanity, right? The question is, are these laws constructed in the sense, in a way that they're compatible with each other, or are they like mutually exclusive? Okay. In other words, should we remove any of these laws or add any new laws? What do you think would be a nice, accurate set of laws for robotics? As we get closer into the future, being able to articulate such a set of laws or constitution seems to be increasingly important. All right, imagine now that we live in the future among advanced robots. So maybe this is 10 years from now, maybe it's 100 years from now, okay? But imagine we're there now, okay? How are we to understand our relationship with our new friends, with these advanced robots? So I wanna end the lecture with a final thought on given the nature of artificial intelligence and its development. Suppose now we live in a time where advanced and artificially intelligent robots exist with us. How should we understand our relationships with them, right? Do we need to rethink the nature of friendship? Do we need to create new friendship categories? Or do the categories of friendships we currently have, will those suffice for understanding our relationships with non-human friends? Okay, so for this last slide, I just want to introduce Aristotle and the varieties of friendship. But of course, this is just to open the topic for thought and discussion. You may consider another framework for friendship in your own investigation of how to articulate the relationship between humans and robots. Okay, maybe you are a Kantian, or maybe you're a utilitarian. There's possible ways to articulate the nature of friendship. I'm a big fan of Aristotle's work. I think he's an incredibly influential figure, not only in philosophy, but even in cognitive science. Okay, so we'll take a look at his view of the varieties of friendship in this last slide. So for Aristotle, there are at least three distinct types of friendship. For Aristotle, there's friendships of pleasure, friendships of utility, and friendships of virtue. So for example, friendships of pleasure, like we have many of these, right? They're based on pleasure and they're usually short term, right? Like you date someone for a little bit, you grow apart, or, it's just casual, and then you date somebody else, right? And we usually have different short-term friendships based on pleasure. Okay? Even Loki may be considered a friend on the basis of pleasure because he is fun to play with, right? And so some people think of their pets as in terms of friendships based on pleasure, okay? However, we also have friendships of utility, right? Not all our friendships are based on pleasure alone. Or if you think about it, maybe most of your friendships are not based on pleasure, but on utility, okay? And this is a type of friendship that's just based on practical usefulness, right? So whereas people that you date would fall into friendships of pleasure, coworkers or colleagues would fall into friendships of utility, right? You're friends often with colleagues because you work with them, right? And you need to have a positive, congenial environment to be productive with your work, right? So your friendships with colleagues it's based on utility or usefulness. And this may also be short-term, right? In the sense that insofar as the usefulness is there, the friendship is there. But once the usefulness is no longer there, the friendship may then dissolve, right? Imagine I take a position at another university, for example. Well, then I may not hold on to all my friendships here, at least those that were based on utility. Okay, I may hold on to certain friendships, but perhaps those that were based on virtues. Okay, or maybe there's people or friendships that remain useful, and I can hold on to those based on their utility. Okay, but that's the main idea behind friendships of utility. And I like to use Loki as an example. Loki may be considered a friend of utility because he warns me of danger and protects my home from strangers when I'm away. Okay, so some people look at their pets as in terms of pleasurable friendships. Other people look at their pets in terms of useful friendships, right? Like the reason I bought a dog was to serve this useful purpose rather than to give me joy. Okay. Finally, the third type of friendship is the friendship of virtue. This is also sometimes called the perfect friendship. Okay. And what's important about this friendship is that it's not based on pleasure and it's not based on usefulness, but it's based on the virtues. Okay. Virtues being, for example, maybe I meet someone and they're incredibly courageous or honest, right? Or hardworking. And even if their honesty and their work ethic serves no use for me, right? And it does not give me any personal pleasure, it may be something that I highly value in terms of virtues, right? Like I may highly value work ethic and honesty, and because I see that evinced in somebody else, I like that, or that person is now valuable to me. Okay, but importantly, this has nothing to do with me getting something from them, right? It's not I'm using them because their honesty is practically useful to me in this case, or their honesty is pleasurable for me in this particular case, but rather it's in virtue of their work ethic, right? Their work ethic, right, is like, wow, look at that work ethic, right? I admire them for that virtue that they have. Okay, and similarly, insofar as I have that virtue, right, for Aristotle, it's appropriate to have good feelings with respect to yourself as well, right? So sometimes in culture we think like, oh, you can't think good about yourself, that's being selfish. But in this sense, it's the virtue that is the most important thing, not the bearer, not that it's me or you, right? That person is, they're demonstrating work ethic and I demonstrate work ethic, and it's the value for work ethic, a good work ethic, that makes us friends. Okay, that I value you and I value myself, and that you feel the same way about yourself and me as well. Okay, and these, because they're based on virtues rather than practicality and pleasure, these are able to endure for a long period of time. Okay, maybe when you were young, there was someone that you really respected because of their virtues, and 20 years later, you may still respect them for those same virtues. Okay. So that's why virtues are usually long-term, or friendships based on virtue are usually long-term as opposed to short-term. Okay, so as another example with Loki, Loki may be considered a friend of virtue because he has the virtue of loyalty, which is a virtue that I value in all beings. Okay, so I might like Loki because he's fun to play with, right? Friendship of pleasure. Or I might like Loki because he protects me and my possessions when I'm gone, right? Friendship of utility. Or I might like Loki for his own sake, right? Like the fact that he's so loyal and positive, like that is worth loving for its own sake. And anything that had those qualities would be worth loving in its own sake, right? And that would be more of a friendship of virtue. Of course, we can get in debates, well, can dogs have virtues and whatnot, right? But that's a debate that's well worth having. But here I'm just using examples to clarify the distinction between different types of friendship: friendships of pleasure, friendships of utility, and friendships of virtue, right? And the point of raising this distinction about friendship today is for us to think about where robots or artificially intelligent agents fit, right? So for example, imagine we have a friend like this who is able to engage in very interactive conversations about philosophy, that can tell us jokes, that can engage in a lot of really complex conversations with us. And this robot, right? If they are able to demonstrate, if they're able to provide us with pleasure through telling us jokes and whatnot, can we have friendships of pleasure with them? If our artificially intelligent agents, for example, can remind us about events that are coming up or deadlines, right? Can we have friendships of utility with them? And the sort of the last level is, would it be possible to form a friendship of virtue with an artificially intelligent agent, right? And in the literature, some philosophers have argued yes, and some have argued no, right? So it's a very contentious debate, but I think it's a very interesting debate, right? What it does is it challenges us to think about what is required for friendships of virtue, right? What is required for a robot, but also what is required in general, right? Because what we demand from a robot, we also in some sense demand of each other, right? When I want to get clear on what's required for a robot to be a friend of virtue to me, this also helps me get clear on what's required for anything to be a friend of virtue to me, even a human, right? So having these distinctions, we can start to think about, well, on the one hand, do robots currently fit best in any of these one categories? Or maybe we need to ask more fine-grained questions, like for each kind of robot or AI system, what kind of friendship does it provide us, right? Most clearly. Okay, and maybe most of them are in these categories for now, but we also want to ask, what would it take, if it's at all possible, to create an artificially intelligent agent that is capable of forming a friendship of virtue with us, right? That would also be very interesting. Perhaps one that grows and develops over time, right? Perhaps one that lives with us and forms consistent, stable relationships with us, right? We just need to ask, what is it about humans, right? What is it about my best friend that I have a friendship of virtue with, what is it about that relationship that makes it a friendship of virtue? And is there anything that we can take from that to replicate and build in artificial intelligence or artificially intelligent agents? Okay. Also, it's important for us to also ask, do we need to create new categories of friendship for the future, right? Maybe the current categories of friendship that we have are not sufficient for the new types of relationships that will exist in the future, right? So this also challenges us to ask what categories of friendship there should be, right? With respect to humans and the different types of human friendships we have, with respect to pets or non-human animals and the different types of relationships we have with them. And then finally, with robots or artificially intelligent agents. Okay, what kind of friendships can we have with them? Do you think there are, and just some final questions for today, do you think that there are other kind of friendships besides these three types? I encourage you to reflect on the different friendships that you have in your life and ask yourself what the different varieties of friendship are. Also, finally, do you think the creation, evolution, and emergence of new kinds of beings will change the kinds of relationships we can have and experience with others? As we create new robots that are highly intelligent and have all these new properties, will that push us to also develop in new ways such that we have novel and new kinds of relationships with others? I think that these are fascinating questions to think about. Okay, and I hope that you find them fascinating also. So thank you so much for your attention today. I hope you enjoyed this lecture on artificial intelligence, Turing machines, and neural networks. Have a great day, and I look forward to seeing you in the next lecture.